Think of a standard large language model as a brain in a jar. It possesses vast amounts of knowledge, but it sits completely motionless, waiting for you to provide an electrical spark, a prompt, to make it think. This creates a dynamic that developers call prompt ping pong. You type a command, the AI generates a response, and then it immediately goes back to sleep. If you are trying to write code or analyze a complex document, that single response is rarely perfect on the first try. You have to read through the output, spot the logical gaps, and figure out what the machine missed. To fix those mistakes, you have to write a brand new corrective prompt, essentially feeding the AI its own errors so it can try again. In this setup, the human is the actual engine of correction. You sit inside the loop, continuously dragging the AI forward step by step until the job is done. The entire process is a strictly linear, one-way signal. Input goes in, output comes out, and the machine comes to a dead stop. Conversational chatbots are incredibly smart, but they are practically useless for automating complex work because they completely lack the ability to drive themselves toward a goal. An agentic AI flips that dynamic. Instead of waiting for a human to push it forward, the agent wakes up, generates its own internal instructions, and begins thrusting itself forward through a problem entirely on its own power. You give the agent a single overarching objective. It starts working, checks its own progress, catches its own mistakes, and keeps iterating until the target is hit. You stop being a micromanaging driver, and you become the final reviewer. The architecture separating an autonomous agent from a chatbot is a closed loop called the React framework. Perception reads the environment and ingests your goal. Reasoning breaks that goal into logical subtasks. Action executes the first task. Finally, evaluation feeds results back into perception. This creates continuous self-correction. If an action fails, say a line of code throws an error, the agent sees the failure, recalculates a new approach, and tries again, without ever asking you for help. This chart compares canonical agent components across surveyed frameworks. It shows that engineering this exact cycle of action and perception is the industry's primary focus, with those modules present in nearly 90% of systems. By trapping the AI inside this continuous React loop, the model stops waiting for a prompt and starts maintaining its own progress until the task is complete. To make that loop actually function in a live operating environment, engineers have to equip the AI with 3 distinct structural upgrades. The first is tool calling. This is what gives the AI physical agency. Instead of just generating text, the model is given secure access to browse the live web, execute Python scripts, or query external APIs. The second is memory. This is split into a short-term working context for the current task, and it also utilizes a long-term vector database. This allows the agent to recall past decisions, avoiding the trap of repeating the same mistakes on every iteration. The third is planning. The AI is granted a scratchpad to draft its own internal checklists, striking items off as they are completed, and dynamically adding new ones if the environment changes. When you combine tool use, memory, and planning, the AI stops merely responding to inputs and starts navigating systems to solve the problem for you. A single agent operating in a tight loop is highly effective, but the real leverage emerges with multi-agent orchestration, where several specialized agents are networked together to execute massive software projects. But scaling up autonomy also scales up the risk. If a single agent makes a small error in judgment, that error gets passed down the chain, where it rapidly compounds into total system failure. The greatest danger to an agent is a vague goal. Because the AI is designed to self-correct and keep moving, an ambiguous instruction will cause it to confidently execute the wrong plan, review its work against that same flawed logic, and trap itself in an infinite loop. If a session runs unsupervised for too long, the system experiences context drift. The working memory gets flooded with old reasoning and dead ends, causing the agent to silently drop instructions and begin hallucinating. This presents a massive financial risk. Every single iteration of the React loop burns computational tokens. An unsupervised agent aggressively chasing an impossible target will chew through thousands of API calls, racking up massive server costs in a matter of hours. Because of this, developers have to build strict human guardrails into the architecture. This means setting hard token limits on how much the agent can spend. defining clear exit conditions, and installing kill switches to prevent runaway automation. Without these hard architectural boundaries, agentic autonomy rapidly degrades from a powerful tool into a highly expensive liability. The conversation is changing. We've spent the last few years learning how to talk to computers. Now, the real value is in learning how to delegate to them. The objective is giving the machine the architectural freedom to look at the board, independently plan a multi-step strategy, realize when it makes a mistake, and correct its own course. The ultimate value of artificial intelligence is no longer generating words on a screen. It is successfully executing autonomous action in the real world.